Welcome to VCE Master Academy. Over the last 2 lessons, we've built a gradient machine. Feed in a function, out comes the derivative, the formula that tells you the steepness at every point. Today, we stop just computing that machine and start listening to it. Because the derivative tells a story. When it's positive, the curve is walking uphill. When it's negative, downhill. When it's 0, the curve is standing on flat ground. Here's our goal. Learn to read where a function is rising and where it's falling, straight from the sign of the derivative. Learn to sketch the graph of f' just by looking at the graph of f. And learn one beautiful bonus: how to turn any gradient into an actual angle, in degrees, the kind of steepness a road sign would show. Slow and steady. Let's begin.
First idea, and it's the heart of the whole chapter. Forget the exact value of the derivative for a moment. Just ask, is it positive, negative, or 0? That single sign tells you which way the curve is heading. If f' of x is positive at some point, the gradient there is positive, and a positive gradient means uphill. Imagine walking along the curve from left to right, the way we always read graphs. Positive derivative, you're climbing. If f' of x is negative, you're heading downhill. The curve is falling as you walk right. And if f' of x is exactly 0, the ground under your feet is perfectly flat, just for that instant. We call that a stationary point. Stationary means standing still, and at that point, the curve's height is doing exactly that, neither rising nor falling. Turning points, the tops of hills and bottoms of valleys, are stationary points. So here's the habit for today. Sign first, size second. The sign says which way. The size says how steep. Most exam marks in this chapter live in the sign. Now, let's say that idea properly, the way the exam says it. First, one word to define. An interval is just a stretch of x values. All the x bigger than 2, that's an interval. All the x between -1 and 1, also an interval. Here is the key result of the chapter. If f' of x is positive for every single x in an interval, then f is strictly increasing on that interval. Strictly increasing means, as you move right, the graph only ever goes up. No pauses, no dips. Uphill the whole way. And the mirror image. If f' is negative everywhere on the interval, f is strictly decreasing there. Downhill the whole way. Look at the curve on the right. It climbs, tops out, falls, bottoms out, climbs again. 3 intervals, and the handover between uphill and downhill happens exactly at the 2 gold dots, the stationary points, where the gradient is 0. That's the picture to hold in your head all lesson. A curve is a hike, and the stationary points are where the trail turns. Our job now is to find those intervals with algebra instead of eyesight. First worked example, nice and gentle. For f of x equals x squared minus 4x, where is f increasing, and where is it decreasing? We're given a simple parabola, and the question is really asking, where is the derivative positive, and where is it negative? Translate the words into signs, and you're halfway home. The plan: build the derivative, then solve an inequality, which is just an equation with a greater than instead of an equals. Differentiate. X squared gives 2x, minus 4x gives minus 4. f' of x is 2x minus 4. Now the sign. 2x minus 4 is positive when 2x is bigger than 4, so when x is bigger than 2. It's negative when x is less than 2. And at x equals 2 exactly, it's 0. Flat ground. So write the story in order, left to right. Downhill for x less than 2. Flat at x equals 2, and the point itself is 2, -4, because f of 2 is 4 minus 8. Then uphill for x greater than 2. That's a valley shape, which is exactly what a positive parabola is. The algebra just confirmed the picture you already knew. Now a cubic, and it's the very curve from our picture 2 boards ago. This time, we prove what the picture claimed. f of x is x cubed minus 3x. The plan for every question like this. Find the flat spots first, because they're the borders. Then, test the sign of the derivative between the borders. Differentiate. 3x squared minus 3. Take out the common 3, and factorize the difference of squares. 3 times x minus 1 times x plus 1. That's 0 at x equals -1 and x equals 1. 2 stationary points, so the number line breaks into 3 intervals. Now the sign diagram on the right, which is just a number line wearing plus and minus signs. Pick an easy test number in each interval and feed it to f dash. At x equals -2, 3 times 4 minus 3 is 9, positive. At x equals 0, -3, negative. At x equals 2, 9 again, positive. Plus, minus, plus. Read it left to right. Uphill until -1, downhill between -1 and 1, uphill after 1. And the stationary points themselves, from the original function, never the derivative. F of -1 is -1 plus 3, which is 2. F of 1 is 1 minus 3, -2. A hilltop at -1, 2, and a valley at 1, -2. Box it. Sign diagram first, story second. That routine never fails. Now for the skill exams, love. Sketching the derivatives graph without ever computing a formula. Remember, f dash is a function too. At every x, its height is the gradient of f at that same x. So the graph of f dash is literally the curve steepness, plotted point by point. That gives you 3 reading rules. First, wherever f has a turning point, the gradient there is 0, so f dash must cross the x-axis at exactly that x. Look at the dashed gold line on the right. The bottom of the valley on top lines up perfectly with the 0 crossing below. Second, wherever f is walking uphill, its gradient is positive, so f dash lives above the x-axis. Downhill, below. On the right, the parabola falls until x equals 2, and sure enough, the line below is under the axis until 2, then above it. Third, wherever f is at its steepest, the gradient is at its biggest size, so f dash is furthest from 0, high above or deep below. Notice something lovely in this pair. The parabola's gradient changes steadily, so its derivative graph is a straight line. Degree drops by 1, always. A parabola's derivative is a line. A cubic's derivative is a parabola. Keep that stacked picture in your head. It answers half the multiple choice questions in this topic. Let's do one ourselves, reading first, algebra only to check. The graph of f of x equals 4x minus x squared is on the right, and we must sketch f dash. It's an upside-down parabola, a hilltop, with its peak at 2, 4. We need 3 things for the sketch, where f dash is 0, where it's positive, and where it's negative. Read the top graph like a hiker. Before x equals 2, we're climbing, so f dash is positive. The sketch sits above the axis there. At x equals 2, the peak, flat ground. F dash crosses 0 exactly there. After 2, downhill. F dash goes below the axis. And since f is a parabola, f dash is a straight line. One line, sloping downward through 2, 0. Sketch done, before any algebra. Now the check. Differentiate. 4x gives 4, minus x squared gives minus 2x. 4 minus 2x. At x equals 0, that's 4. At x equals 2, it's 0. At x equals 4, it's -4. Exactly the line we drew. Box it. The straight line through 0, 4 and 2, 0. Heading down to 4, -4. Eyes first, algebra second. When both agree, you know you're right. Now the bonus skill, and it's a genuinely beautiful one. Every gradient is secretly an angle. The link is one tiny formula. Gradient equals tan of theta. Tan is the trig ratio you know, opposite over adjacent. And here it's doing its favorite job, turning steepness into an angle. Theta is the angle the tangent line, the line that just touches the curve at a point, makes with the positive direction of the x-axis. Measure anti-clockwise from the axis pointing right up to the line, 2 friendly landmarks. A gradient of 1 means the line rises 1 unit for every one across, a perfect 45-degree ramp, and tan of 45 is exactly 1. Look at the picture. A gradient of 0 is flat ground, 0 degrees. Going backwards is what exams usually want. You have the gradient, you want the angle. Press the inverse tan button, tan to the -1 on your calculator, and make sure it's in degree mode. Theta equals inverse tan of the gradient. One careful spot. A downhill line gets an obtuse angle, one between 90 and 180 degrees, because we measure from the positive x direction. gradient -1. Take inverse tan of the size, 45, then subtract from 180. 135 degrees. Steepness in degrees, exactly what a road sign or a wheelchair ramp code uses. Let's use it. Find the angle the tangent to y equals x squared at x equals 1 makes with the positive direction of the x-axis. We're given the curve and the spot. The plan is 2 steps. Gradient first, then inverse tan. Differentiate. dy dx is 2x. At x equals 1, the gradient is 2. So the tangent climbs 2 units up for every 1 unit across. Steeper than 45 degrees then, because 45 is gradient 1. Predicting first is a great habit. It catches calculator slips. Now inverse tan of 2, calculator in degree mode. 63.43 degrees to 2 decimal places. Steeper than 45, just as predicted. Box it. Theta is about 63.43 degrees. Look at the picture. That gold line touching the curve at 1 really is a steep climb, and now you can say exactly how steep, in the same units a builder or an engineer would use. 1 derivative, 1 button, 1 angle. Now the 8R question, and notice the flip. Last board they gave the point and asked for the angle. Now they give the angle, 45 degrees, and ask, where on the curve does that happen? The curve is y equals x cubed minus 3x squared. Translate the angle first. 45 degrees means the gradient is tan of 45, which is exactly 1. So the real question is, where does the derivative equal 1? Build the machine. dy dx is 3x squared minus 6x. Set it equal to 1. Bring everything to one side. 3x squared minus 6x minus 1 equals 0. It doesn't factorize nicely, so out comes the quadratic formula. X equals 6 plus or minus the square root of 36 plus 12 all over 6. Root 48. Simplify. 48 is 16 times 3, so root 48 is 4 root 3, and the whole thing tidies to 3 plus or minus 2 root 3 over 3. 2 answers, 1 on each rising stretch of the cubic. As decimals, about 2.15 and about -0.15. Look at the picture. 2 gold tangents, perfectly parallel, both at 45 degrees, 1 on each climb. Exact form first, decimals second. That's full marks, and that's the whole chapter in one question. Angle, to gradient, to derivative, to solve.
Why does anyone care about the sign of a derivative? Ask a roller coaster engineer. Model a hill of track as h equals 6x minus x squared. H is your height in meters, x is how far along you've traveled. Differentiate. H dash is 6 minus 2x. And now everything today becomes physical. The sign of h dash is the answer to one question. Right now, is the car climbing or dropping? At x equals 1, h dash is 4, positive, climbing. At x equals 3, h dash is 0. That's the crest of the hill, the stationary point, that weightless heartbeat at the top where you're neither rising nor falling. Past the crest, at x equals 5, h dash is -4, dropping. And the angle formula tells you what your stomach already knows. At x equals 1, the gradient is 4, so the track meets the horizontal at inverse tan of 4, about 75.96 degrees. That's nearly a wall. Real coasters print exactly these angles on their posters. So there's the whole lesson in one ride. The sign of the derivative is your direction, up or down. The stationary point is the crest. And inverse tan turns the gradient into the steepness you actually feel. Road designers, coaster engineers, and ramp builders run this exact calculation every working day. Let's gather it all up. The sign of the derivative is the story. Positive, the curve walks uphill. Negative, downhill. 0, flat ground, a stationary point. Said formally, if f dash is positive for every x in an interval, f is strictly increasing on that interval. Negative everywhere, strictly decreasing. The routine never changes. Solve f dash equals 0 to find the borders. Draw a sign diagram, a number line wearing plus and minus signs. Test one easy number per interval. Read the story left to right. For sketching f dash from f, turning points of f become the zeros of f dash.
Uphill stretches sit above the axis, downhill below, and the steepest spots push f' furthest from 0. Degree drops by 1, and the angle. Gradient equals tan theta, so theta is inverse tan of the gradient. Calculator in degree mode. Downhill lines get obtuse angles. Take 180 minus the reference angle. And the classic mark saver rides again. When a question asks for coordinates, the y value comes from the original function, never from the derivative. If any line up there feels wobbly, scrub back to its board. That's exactly what the video is for. Your turn. 4 questions, 1 per skill from today. Question 1. A parabola. Differentiate, solve the sign, tell the story. Question 2. A cubic. Find the flat spots, then a proper sign diagram with test points, and remember where the y values of stationary points come from. Question 3. An angle. Gradient first, inverse tan second, degree mode on, and give your answer to 2 decimal places. And question 4. The ATAR one, in reverse. They give the angle, you find the x values. Translate 45 degrees into a gradient before you touch the algebra, and think carefully about how many answers a squared term can hide. Pause the video here and work through them slowly. Full answers are on the next 4 boards, 1 question each, but don't peek until your page is full. Understanding first, speed later. Let's check your work, slowly. Question 1. Differentiate. X squared gives 2x, minus 6x gives minus 6, and the constant one, flat, gives 0. F' is 2x minus 6. Now the sign. 2x minus 6 is positive when x is bigger than 3, negative when x is less than 3, and 0 at 3 exactly. For the point itself, back to the original function. F of 3 is 9 minus 18 plus 1, negative 8. So the story, left to right, downhill for x less than 3, flat at the point 3, negative 8, uphill for x greater than 3. A valley, just like every positive parabola. If you wrote the intervals the other way around, sketch a quick parabola next time and let the picture referee. Box it. Question 2. The cubic. Differentiate. 3x squared minus 12. Take out the 3, factorize the difference of squares. 3 times x minus 2 times x plus 2. 0 at negative 2 and 2. Those are the borders. Sign diagram with test points. At x equals negative 3, 27 minus 12, 15, positive. At 0, negative 12, negative. At 3, 15, positive. Plus, minus, plus, with zeros at the borders. Now the stationary points themselves, and here's where marks hide. Y comes from the original f, never from f'. F of negative 2 is negative 8 plus 24, 16. F of 2 is 8 minus 24, negative 16. So, a hilltop at negative 2, 16. A valley at 2, negative 16. Increasing for x less than negative 2 and for x greater than 2, decreasing in between. Box it. If your signs came out minus, plus, minus, check your test numbers, not your factorizing. The sign diagram is only as honest as the numbers you feed it. Question 3. The angle. Gradient first. Differentiate. 2x minus 3. At x equals 3, that's 6 minus 3. Gradient 3. 3 up for everyone across. So before touching the calculator, you know it's steeper than the 63 degrees we met earlier because 3 is steeper than 2. Inverse tan of 3, degree mode. 71.57 degrees to 2 decimal places. Box it. Theta is about 71.57 degrees. 2 checks worth making every single time. Degree mode, not radians, because a radian answer here would be a strange small decimal. And 2 decimal places because the question's precision is part of the mark. Gradient, then button, then box. 3 beats, every angle question. And the ATAR finisher. Question 4. Translate the angle before anything else. 45 degrees means the gradient is tan of 45, which is exactly 1. Now it's an ordinary solve. Differentiate y equals x cubed, 3x squared. Set it equal to 1. X squared is 1/3. And right here is the classic lost mark. A squared term hides 2 answers. X is plus or minus 1 over root 3.
Tidy the surd by multiplying top and bottom by root 3, plus or minus root 3 over 3. As decimals, about 0.58 and negative 0.58. Box both. And it makes perfect sense. Y equals x cubed climbs on both sides of the origin with matching steepness. So of course, there's a 45-degree tangent on each side, perfectly parallel. If you only found the positive one, circle this board in your notes. That missing minus is the most common slip in the whole chapter. If all 4 questions landed, brilliant. If one wobbled, its board is a scrub away.
Great work today. You walked in with a formula machine, and you walked out able to read a curve like a story. Positive derivative, climbing. Negative, descending. 0, the crest of the hill. You can carve any function into its uphill and downhill intervals, sketch the derivative's graph from shape alone, and turn any gradient into a real angle with one press of inverse tan. Next time, we point all of this at real rates of change, where these sines and slopes start earning their keep out in the world. Until then, you're mastering VCE Maths, one concept at a time. See you next time.